Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the Carnot vapor cycle. In Project 10, we discussed gas power cycles for which the working fluid remains a gas throughout the entire cycle. In this project, we consider vapor power cycles in which the working fluid is alternately vaporized and condensed. We have mentioned repeatedly that the Carnot cycle is the most efficient cycle operating between two specified temperature limits. Thus, it's natural to look at the Carnot cycle first and the prospective ideal cycle for vapor power plants. If we could, we would certainly adopt it as the ideal cycle. As will be explained, however, the Carnot cycle is not a suitable model for power cycles. Throughout the discussions, we assume steam to be the working fluid since it is the working fluid predominantly used in vapor power cycles. Consider a steady flow Carnot cycle executed within the saturation dome of a pure substance as shown in Figure A. The fluid is heated reversibly and isothermally in a boiler, expanded isentropically in a turbine, condensed reversibly and isothermally in a condenser, and compressed isentropically in a compressor to the initial state. The Carnot cycle is not a suitable model for power cycles because in Figure A, the isothermal heat transfer to or from a two-phase system is not difficult to achieve in practice since maintaining a constant pressure in the device automatically fixes the temperature and the saturation value. Therefore, process state 4 to state 1 and state 2 to state 3 can be approached closely in actual boilers and condensers. Limiting the heat transfer process to two-phase system, however, severely limits the maximum temperature that can be used in the cycle. Limiting the maximum temperature in the cycle also limits the thermal efficiency. Any attempt to raise the maximum temperature in the cycle involves heat transfer to the working fluid in a single phase, which is not easy to accomplish isothermally. The isentropic expansion process can be approximated closely by a well-designed turbine. However, the quality of the steam decreases during this process, as shown on the TS diagram in Figure A. Thus, the turbine has to handle steam with low quality, that is, steam with a high moisture content. The impingement of liquid droplets on the turbine blades causes erosion and is a major source of wear. Thus, steam with qualities less than about 90% cannot be tolerated in the operation of power plants. This problem could be eliminated by using a working fluid with a very steep saturated vapor line. The isentropic compression process involves the compression of a liquid-vapor mixture to a saturated liquid. There are two difficulties associated with this process. Firstly, it is not easy to control the condensation process so precisely as to end up with the desired quantity at stage 3. Second, it is not practical to design a compressor that handles two phases. Some of these problems could be eliminated by executing the Carnot cycle in a different way as shown in Figure B. This cycle, however, presents other problems such as isentropic compression to extremely high pressures and isothermal heat transfer at variable pressures. Thus, we conclude that the Carnot cycle cannot be approximated in actual devices, as is not a realistic model for vapor power cycles. Okay, that's all for this task. Thank you very much and see you next time.